Okay, so in the previous videos which you've watched so far, um, you've looked at a bunch of different magnetic fields that were made by particular currents, and there were a bunch of equations that were basically just handed to you, and you can use them to find the magnetic fields made by currents in particular configurations. But this is actually looking at what are the laws underlying that, and so that you can, in a pinch, if you have a current that is in a sort of configuration that is not exactly what you've seen before, you could still find the magnetic field that it makes. And so this is going to be very similar in structure to the first part of the course, where we'll derive some of these, and the magnetic field formulas will just live on the equation sheet, and you can just use them. So make sure you get comfortable with what is there so that you can just grab at it whenever you want. And then that's what you'll do for a good chunk of the homework. If you see something familiar, just grab the formula. And then, of course, you'll need to know how these new laws that we're going to introduce here are working well enough so that then if you get an unfamiliar looking current, a current that is made by a wire that's wrapped in some unusual way or something like that, then you can go ahead and find that magnetic field yourself. So let's talk about how you would do that. So just as a reminder, charges make electric fields and currents make magnetic fields. And so the two laws that we're going to introduce very much have a counterpart in what we did before. So over here you'll probably recognize this. This was kind of the cornerstone of homework number 2, where you were breaking an object into small dqs, and every single one of those can be considered a point charge and contributing a small bit to the electric field dE. And so of course we know how a single point charge then behaves, and then we're going to assemble some other whatever shaped object out of a bunch of those little dqs. So that's how we find the electric field of the whole thing. So it's just, if you know how to find the electric field of one thing, one point charge, a small bit of charge dq, which is dE, then you can go ahead and put the whole thing together. I'll call that the direct integration approach. Again, we looked at this in homework number 2. This particular formula didn't have any name or anything like that. It's just kind of a, it essentially comes from Coulomb's law, but it's just taking the differential form. So it's a dq making a dE instead of a q making an E. And there is a magnetic version as well. This does get a name. It's called the Biot-Savart law. And it looks very complicated. dB equals mu naught over 4 pi I dl cross r hat over r squared. Don't get intimidated. At the heart of it, what it's saying is that a current here will make magnetic field. So again, current will make some small contribution, then we're going to integrate. So these are kind of the direct integration equivalents, the kind of brute force integration. So if you have, say, some crazy shaped wire with a current I flowing through it, whatever it's shaped like, what we do is, it's not that the current is small, but we break it in a small segment dl of that current. So that's what this really is here, I times dl. That's kind of like your equivalent of dq over here is I dl. And then of course what we're going to do is we're going to construct the whole wire out of integrating those little segments up. So we get all those little segments and we can construct the whole wire's magnetic field from that. So I'll make a separate video on what's going on with this law and how to use it and so on and so forth, but this is kind of an overview at this point. Now, of course, the direct integration approach, that was kind of took a lot of effort to get that done sometimes. So there are also what I'll call symmetry-based laws. This is what you did on homework 4. Of course, you did Gauss's law. And Gauss's law, when it works, is incredibly great. Of course, it doesn't work in many situations, but If you have a highly symmetric situation, that's why I call it a symmetry-based law, then it works really well. We looked at planar, cylindrical, and spherical symmetries. And of course, in those symmetries, you're doing a flux calculation over a closed surface, and you're not really actually going to integrate or anything like that, because the whole point of using this law is that you have some simple relationship that you can use here. But essentially, the same idea, right? It gets you from Q to the field. That's what we use it for, right? So that's the whole point, is Q make E, okay? So, now Gauss's law in and of itself can be, you might ask, can't we just copy it directly over to a Gauss's law of magnetism? All we have to do is replace electric with magnetic. So over here, instead of E dot dA, it's B dot dA, and then instead of electric flux, it's magnetic flux. And then we find, over on the right-hand side, we find a surprise. Over here it's Q enclosed, but this is always 0. So that's why Gauss's law for magnetism, even though it does exist, is kind of a useless law. Here's why. If we're comparing the two, for Gauss's law we have some charge, and it makes some electric field like this. And if we surround it with a closed surface, remember that's what Gauss's law, right? It's a closed surface. Okay? It's telling us that the magnetic flux is proportional to the charge enclosed, or sorry, the electric flux. So if you have positive charge enclosed, you will count positive flux. That's because, for instance, if these electric field lines start on this positive charge, they'll pass through the surface only once, they'll get counted only on the way out as positive flux, and that's how it works. Here's the problem on the magnetic side. We have said that there is no such thing as a magnetic monopole. There is no such thing as a magnetic charge. Okay? There's no equivalent north pole all by itself, like so, such that if you surrounded this with a surface, a Gaussian surface, and you computed the flux, that you would get a positive result. So this is impossible. This can't happen. We know that there are no magnetic monopoles, and in fact they always appear in pairs, and that is just a symptom of the fact that magnetic field lines always form closed loops. They could also be start and end at infinity, which is just a really large loop, but you can never see the end of a field line, right? You can't just have the field line start somewhere and get going, whereas you can easily do that with an electric field line. So if they always appear in pairs, which is to say they always form closed loops, like so, no matter what kind of closed Gaussian surface you are going to make, let's try it right here, okay? It doesn't matter if it encloses both the north and the south, or just the north, just the south. I do want to point out that every one of these field lines will pass through the surface twice. It'll go in and out. And so what that's going to mean, if you carefully do the integration, you will find that the flux, the magnetic flux calculated across a closed surface, is always 0. That is just a symptom of the fact that magnetic field lines are always closed loops. It's not that different as if you had a plus charge and a minus charge. So for instance, if I had a plus charge and a minus charge of equal amounts, your classic electric dipole, then it's the same thing on the Gaussian surface. If you threw in a Gaussian surface here and you enclose both of them, well then Q enclosed would be 0, and the electric flux would be 0, because essentially when you did this integration across a closed surface, every field line that came out and contributed positive flux, there'd be one that was on its way in and contributed negative. And that's where we would get 0 flux here. the problem on the magnetism side is that's always going to be true. You're going to always get zero flux. If the magnetic field lines are always required to form closed loops, any flux calculation across a closed surface, you're always going to get zero. So essentially, Gauss's law for magnetism, you're always going to get zero no matter what. Sometimes this is also called the no magnetic monopoles rule. And for that reason, it's kind of a useless law for calculation, okay? It doesn't actually functionally do anything for you. This is just a way to state that there are no magnetic monopoles, that magnetic fields always form closed loops. So it's not that the law is wrong, but it's not functionally doing the same thing as Gauss's law does for us over here. So there is another law which functionally behaves similar. So it's not actually Gauss's law on the magnetism, but it is a law which functionally behaves the same. This is called Ampere's law. And Ampere's law looks like this. It's not a flux integral, it's a line integral. So it's asking about what the magnetic field does along a line instead of a surface. The quantity we get is not called flux anymore, it's called circulation. And over here, you can see that it functions very similarly. Over here we have charge enclosed, causes electric field. Here we have current enclosed, which is going to cause magnetic field. And again, it's not that we really ever do this integral. We're going to try to do something very similar. We're only going to really want to use this law if there's some high degree of symmetry. So again, these laws are both symmetry-based. So the only difference here is that this is asking what's the magnetic field's relationship along some closed loop instead of a closed surface. Okay, this symbol here reminds you that it's got to be closed, but here it's a closed area and here it's a closed line. So what this is really about is filling in the gaps of how does the Biot-Savart law work and how does Ampere's law work. And so I'll bounce those out to separate videos, but I do want to point out that both of the formulas have a shared constant. So the shared constant is right here, is mu naught. Okay? So this is already mentioned in the other videos. Mu naught is kind of like your magnetic constant. It is going to appear in all your magnetic field formulas, much the same that K or epsilon naught, this is like your electric constant. You can of course package it up either way as K or as epsilon naught. That's going to be electric constant that appears in all your electric field formulas. So anytime you see a magnetic field formula, it's going to have a mu naught in there somewhere. Anytime you see an electric field formula of something, you're going to see K or epsilon naught in it, depending on what is your preference. So, okay, so let's stop there, and I'll do separate videos talking about Biot-Savart and talking about Ampere's law.